Welcome. In today's episode, we'll discuss vectors in Python and Grasshopper. Let's get started. So let me turn to the canvas, and let's start with vectors. So what is a vector? Well, a vector is really a list of numbers. So let's say we have a. We usually denote it with an arrow at the top, equals, and then we use the same syntax as we use for lists in Python. So we can do like maybe 1, comma 1.2, then 3.6, and this could be a vector. So it's a 3D vector because we have three components, and we can say that, this component is the first one, this is the second one, this is the third one, and they're not interchangeable. Like the position in which they are matters, so they're ordered lists. Another way you could represent the vector is with curly braces. You could probably see this around, and this is a row vector because it's written horizontally. Uh, Many times you will see vectors written vertically, so let's write them vertically. So 1, 1.2, 3.6. All right, so this is the vertical representation. It's a column vector. All right, so we can also use vectors to represent them graphically, so not only as lists. So let's draw maybe a 2D vector, so a vector which only has two components because it's easier to draw. So let's say we have the y-axis, we have the x-axis, and then we have a vector, let's say vector A, which is represented by its two components, one on the x-axis, one on the y-axis. So this would be maybe A1, and this would be A2. So we could write that A is a vector A1, A2. All right, another representation, the last one we'll see about these vectors, is we could use the so-called unit vectors. So we could say that this is I, and this is j, and this represents a vector in the direction of the x-axis and of the y-axis with a length of 1. So this, if we use these two notations, then we can also write that a equals a1 times I, so in the direction of I, plus a2, so this was a1, in the direction of j. So this is another way of representing a vector. All right, so let's go in Python and Grasshopper and see how vectors are handled there. So we are, as always, in our canvas in Grasshopper, and we have our Python interpreter. So let's start probably with Grasshoppers because it's easier and you can see the vectors around. So the vectors are in their specific menu. So there's vector and vector here, and you can vector x, y, z to build vectors. The vectors we'll see in Grasshopper are 3D vectors, so they always have three components, x, y, and z. So let's actually switch to split view so we can actually visualize the vectors in the Rhino canvas as well. Let's define three numbers. We used, I believe, 1, 1.2, and 3.6, but you could use any number. We're using sliders to define the components. So we have x, we have y, and we have z. All right, and we created a vector. We can inspect this vector using a panel as always. So let's drop it in. We have a vector, and indeed this is the vector we defined, and it's given us with these three components. And you will also see that it's using this curly bracket representation. All right, we can also visualize a vector in the 3D scene. And to do that, we need to use under the display menu. Well, actually, let's get there. So the display menu, vector, there's this vector display component. And we can take the vector and drop it in the vector. And then you have to define an anchor. So in our case, it's the origin of the axis. So we will just define another vector. If you write x, y, z, it will prompt you the vector x, y, z component. And by default, if you don't provide any input, these will all be 0. So it's the origin of the axis. And let's drop it into the anchor. And indeed, we see our vector 3D. Let's maybe delete the z component. So it's just a vector in the plane. And then if you move around the y component, you'll see the vector updates accordingly. And of course, you can have negative numbers as well. So let's define the minimum as -10. And then if you go back, you can go back in space. All right, so now that we are here, actually, let me also show you how to define a slider with a negative number, because we didn't see it last time. because if you try to write -3, it will prompt you to do the subtraction. So if you just do -3 and then 2 dots, then it becomes a slider, and if you enter, you can actually get the slider with a negative number in. Okay, and the other properties of sliders still hold using negative numbers, of course. Okay, so we defined a vector. Let's go now to Python and do it in there as well. To do that, we need to import Rhino geometry. So let's import Rhino geometry as RG, so we don't have to spell Rhino geometry all the time. So let me actually maybe enlarge the screen so you can see better. All right, so then we can say A, it's a vector. So we'll do Rhino geometry, vector 3D. There are these differences, like 2D and 3D are just 2 components or 3 components. The difference between D and F really comes to the one is the double, one is the float. It's the precision of how many decimal numbers are stored. In our case, we will use the vector 3D default with the doubles, which is sort of like the float of Python in C#. C# is the language which the API is built on, but we are using a Python wrapper around it. It doesn't matter. Let's just use a vector 3D. And then we can define the components. Let's say 1.2. Let's say 1 and 3.6 is slightly different. It doesn't matter. And then we can print A, and indeed, we will get our vector printed out. Okay, so this is how you do a vector in Grasshopper, and sorry, in Python. Of course, we could also do B equals like just a list, 1.2, 1, and 3.6. This will be a Python list, and we can interpret it as a vector, but then we won't have some of the formulas and operators we'll see to handle easily operations of vectors. Instead, if we use the proper class, the proper type, vector 3D, we will also already have this function implemented for us, so it's easier to use. Let's go back to the whiteboard. All right, and let's go ahead with seeing some operations of vectors, some typical operations. So we have the sum of vectors. So the sum, let's take a vector A, this here, and vector B, say this is vector B. All right, and we want to sum the 2 vectors, so A plus B, and the result of A plus B is taking B, putting it at the end of A. So let's do that. And you see that if you have B at the end of A, this is sort of B as well, and this is also A as well. And you get to a certain point that defines the new vector, and this is the result of the sum. So this is vector C. So it's the result of either taking A and moving B to the end of it and then summing them up, or doing the opposite, because A plus B or B plus A is the same thing, they're commutative. And you can also say, of course, that C equals A plus B, which equals B plus A. All right. And of course, we can do it in the same way. The difference is very similar. So let's say we have, again, vector A and B, the same 2 vectors, vector A and vector B. All right. And we want to do A minus B. So we want to define a vector C, which is A minus B, which in this case will be different than B minus A. So this does not hold, of course, it's not commutative. They're 2 different vectors, but we could say that minus C is B minus A. Let's see it graphically as well so we can understand it better. So let's build the same construction as before. Okay, so this would be, as we said, A, and we can also do in the opposite direction minus A, so it's like the opposite of A, and then B the same thing. So we could do like this is of course B, so this is the direction of B as well, and then we can do maybe this. All right, so if this is B, then this is minus B. So A minus B would be like putting A and then minus B here. All right, so A minus B would be this one, so C, and instead B minus A, we called it minus C, it's this one, and they are the same. I just drew them not particularly well, but they have the same length, they have just opposite direction. So you have either C, which is A minus B, or you have minus C, which is B minus A. All right, so we have sums and and subtractions now. Let's also show the multiplication operation for vectors. There are a bunch because let's see them. So the easiest one is the multiplication by a scalar. So let's maybe draw a set of axes. Okay, x. Let's draw a vector. Let's say this is our vector A, and this vector lies in a certain direction. So we can imagine a line, and you could do n times A. So you could do n, write it like this. You could do n times, sorry, not so, n times A, and n is just a scalar, it's just a number, any floating point number, and the result of n times A is just the same vector but longer or shorter. So it would be, of course, longer like this if n is greater than 1, and it would be shorter this if n is less than 1, and of course it would be the same if n equals 1. Okay, so these are the result of multiplying a vector by a scalar. Then we have the multiplication instead between two vectors. There are 3 types of multiplications we can do. We'll show 2 of them because the third one is not really necessary. They're the inner product, so the inner product, okay, product, let me spell it better, product, okay, also called the scalar product, also called the dot product. So there are 3 different ways to say the same thing. So like you have A dot B, that's why it's called the dot product. And the way you compute it is you do the length of A times the length of B. This is the absolute value symbol. It represents the length when we talk about vectors, times the cosine of theta, which is the angle in between the vectors. So let's draw the case. So this is A, this is B, and this is theta. And indeed what you see is that like this is a number, this is a number, this is a number. So the dot product returns a scalar. So the result of this is a number or a scalar. That's why it's also called a scalar product. All right, and the interpretation of this you could remember from trigonometry. That let's use the dotted line. Okay, here you will remember if this is a square angle, then this is the hypotenuse of the triangle. So this, in terms of numeric values, would be the length of A times the cosine of theta. All right. And so the dot product is kind of A times the cosine of theta. So it's the length of the projection of A on B times the length of B. So that's the geometrical interpretation of the vector, of the scalar product. And it's useful because you could imagine that this would go to 0, like if A were to be, let's say we have A prime were to be perpendicular. So if this were a rectangle, then the projection of A on B would be 0. So also the length of B times 0 would be 0. So you can check if 2 vectors are perpendicular to each other using this dot product methodology. And you could also compute it by like with elements, but it doesn't matter. We don't need to see it, or maybe we can at least. Let's say that A is let's maybe 2, 3. And then B, let's say that B is 4, 5. Okay, so we have 2 vectors. If we want to do the multiplication like with elements instead of using the angle in between them, we could do A dot B. That equals, you have to write it like this in order to work. And then we would have 2 times 4 is 8, plus 3 times 5 is 15, and then we have 23. Okay, so this is the result, and it's just a number, as you see. And in this case, you use matrix multiplication rules of matrices to do the computation, or you could do it with elements like with I and J notation, but that's not really the point of the video, so I'm not going to go through that. Let's see the other types of products we can do between vectors. So one is called the cross product, product, also called a vector product. Okay, and the reason it's called a vector product is because it returns a vector as a result. So let's say we have A, and we write cross B like this, and then we get a certain vector C. Okay, so this will be a vector, and indeed we could visualize it. So let's do that. Let's say we have vector A here, and we have a vector B here. So these two vectors would define a certain plane on which they lie on. Okay, so let's say this is a plane. Let's visualize it better. Okay, and the cross product of A times B, it's a third vector C that is perpendicular to the plane of the first two vectors. And it has the length of, I believe it's equal the length of A times the length of B times the sine of the angle in between them. So this is theta. All right, so this is the vector, and the direction, like if it's looking up or down, depends on the direction in which the two members are. So if you imagine taking A and rotating towards B, if this defines a counterclockwise rotation, then the vector is up. If instead you will have like maybe B on this side, so theta would be something like this, then the C vector would point down. So that's the idea of a vector product. We could also see the rules of calculations by hand with elements as we did before, but that's not again the point. So let's go and see how to compute these two products in Rhino, in Grasshopper and Python. There will also be a the third multiplication. We won't see it. Maybe we'll see it in the future if it has some application, which is called the outer product, which is similar to the inner product, but it's just the opposite of this. So it would be the column vector times the row vector. So if you know the rules of multiplication of matrices, you would remember that in that case, the outer product would become a matrix. But since we didn't discuss matrices yet, I won't cover that in this video. We will see it probably in the future. So let's go back now to Rhino and to Grasshopper. So let's do it in Grasshopper first because it's easier, because you can see the actual results. So let's go vector again, and you will see that in here we have, well, vector x, y, z. We used it to build a vector. Let me just show you, just it's there. You could also take a vector and deconstruct it to its base components with deconstruct vector. So that will give you the three base components you dropped in. Okay, very simple. Then you have unit vector. This just takes a vector and divides it by its length. So we didn't see how to compute the length of a vector. Let's actually see it quite quickly. You have, let's use a 2D vector as an example, because it's very easy, of course. So y, we have x. Let's say we have a vector A like this. If we want to compute the length of this vector, we could use Pythagoras theorem quite easily. So let's say this is maybe, let's call it x, x of A and y of A. And we can easily do the square root of the length of A. It's the square root of x A squared plus y A squared. So very easily you can compute the length of it. So if you do A divided by its length, you would get a new vector in the direction of A, but with a length of 1. So that's unitizing a vector, and that's what we can do with this component. So we just take this, we drop it in, and you will see the length of this vector was 1.19. Instead, the length of this vector, let's maybe display it. So let's take it here, we'll drop it in there, and then you will see we get a new vector. Let's disconnect it and reconnect it. A new vector which is in the same direction but with a length of 1. Okay, so that's the other unit component. Unit x, y, and z, we saw them. They were called I, j, and well, k would be in the z direction quite easily. Let's go back to the desktop. You don't need to see me. All right, then we have vector 2 points. You can just define a vector instead of from components by giving 2 points to the start and the end, and that would define a vector. We don't need to see that. Then we have vector length. We saw just a second ago how to compute the vector length, so with the Pythagoras theorem. And then we have amplitude is the opposite of vector length. So this would mean you take a vector, you give you give a length that you want. So you give a vector, let's say this vector here, and then you say, okay, this vector has a length of maybe 1.6. I want it to be a length 3. So the way you do it is quite easily. You convert it to a unit vector, and then you would just multiply it by a scalar. So you convert it to a unit vector, and then you multiply it by this amplitude value, and you would get the new vector. So quite easy. All right. And then angle between, we'll see it later, because I want to show you first in the whiteboard. Let's see the dot and the cross product, which we saw just a second ago. So let's define two vectors. So let me delete a bunch of stuff from the canvas here. Let's define two vectors. So one we have already. Let's maybe make it positive just because. Okay. And then let's define another vector here, which will be maybe the same but with a longer. Okay, like that. Let's do 0.5 here. Okay, so here we have another vector, fine, and then we can do the dot product between the two vectors. So let's do the first one, which is the one at the bottom, multiplied by the second one there, and we get the dot product, in this case 1.4. Let's actually take the same values we did in the example first. So 2, 3, 4, 5, just to check. So 2, 3, 4, and 5. Okay. There. This. Okay, so we'll take 2, 3 is the first vector, like that. 4, 5 was the second vector, and indeed we should get 24 out, 23, sorry, and we get 23, which is what we expected to have. Let's also test if two vectors are perpendicular to each other, give us a 0. So to do that, we will just say that we have a vector just in the x component, just with the x component, and another just with the y component. This should be 0, and indeed the dot product is 0. And we can also now check the cross product. So let's do cross product there. Okay, let's maybe bring back our components x and y. So let's do y, x. All right, and we will compute the vector product. So the first times the second one, and indeed we remember that this is a vector as well, so we can visualize it, and we get a new vector which is pointing down, and the reason is that I would expect that to point up. Check A and B. So A is, okay, I believe A is the one at the top. Let me just check. Vector display. So this vector, yeah, okay, this vector is A. So as you see, if you move from A to B, you go clockwise direction, and indeed, since it's clockwise, the vector is pointing down, so it's what we expected. If you change the A vector to be lower, let's make it like this. There, in this case, from A to B, you go counterclockwise, so it's pointing up, as one would expect. And of course, you can see that if two vectors are parallel, so let's do maybe 2, 1 and 4, 2. So this would be like the same vector, but with the double of the length. Then the length of the vector of the cross product would be 0. So that's what the cross product is used for, and computing if two vectors are parallel to each other. So we have perpendicular with dot product and parallel with the cross product. All right, so then reverse is the same. Of course, we can see it as well in Python. So let's say we have two vectors. Let's define the same two vectors just because. So we have 2, we have 3, and we had 0 in Z. And then we have another vector. Let's call it B. Write a geometry dot vector 3D. And then we have 4, 5, 0. And then we have C is the dot product. This is just simply A times B, like this. Instead, the dot product, it's, C, let's say C2, so this is C1. Okay, it's, you have to call a function, so you go vector 3D dot and cross product. and then you give it the two vectors, so A and B, and these would be the dot product, and we can print C1 and C2, and we can see the result. Indeed, 23 is the result of the dot product, and 0, 0, minus 2 is the result of the cross product, which is the same as we got in Grasshopper. All right, then as I was mentioning, reverse is just like if A is the vector, minus A is the reverse, which is the one we used for sums. And I mean, I haven't mentioned it, but it's pretty obvious, but let's just show it just because. If you take the plus operator, which we saw in the basic math video, and you do the sum of two vectors, you will get the proper summed vector, and the same would be for the difference. And also for division and multiplication, that's like the scalar multiplication that we saw on the canvas, on the whiteboard. And yeah, so they work just fine as well with the basic operators. All right, so the last one I wanted to show you is just this, well, this rotate, not really. I need this angle. They're very similar. So let's just go briefly to the whiteboard again. So the angle between two vectors, how do we compute it? Well, we already have a hint of this because we have the angle like this angle theta in the formula of the dot product. So we can actually derive it from here quite easily, because if we knew the cosine of we can actually derive, like if we knew the length of these vectors, which we can compute, and the actual vector positions, we could derive the angle, the cosine of the angle, and so the angle theta. So the formula for it is theta is the arc cosine, which is just the angle at which the cosine gives a certain value, and the value would be A dot B, so the dot product of A and B, divided by the product of the lengths of A and B, so A and B. And indeed, you see that's just let me write the dot product formula again. Dot this equals A, B, and the cosine of theta. You see this is just the inverse formula, so we just took this one and put it underneath, and then we had the cosine of theta, so the inverse of the cosine then became the angle theta. So this is just a quick way of computing the angle between two vectors, and indeed Grasshopper gives us the option to do it automatically. So let's just take angle, and then we get two vectors. Let's use the same two vectors we have here, vector 1 and vector 2, and indeed we get angle in radians, of course, so we can compute it in degrees as well, and that would be 80 degrees. Let's see which vectors we have. Actually, it's 0 at the moment, so it's 8 to the e of minus 7. So let's just make two vectors which do have an angle in between them. Otherwise, it's kind of boring. Okay, and indeed, in this case, we get 19, and we would also get the reflex angle. Let's do it in degrees as well. The reflex angle, which is just 360, like the full circle minus the angle that we get. And there is a way to do it in Python as well using the API. I don't remember it exactly. Let's see if I can find it quickly. Otherwise, we'll just end here. So let's say if it's called angle between. I believe it's vector angle like this. And then we have an angle. We can print it like that. And indeed, we have an angle in radians, which we could like convert to degrees quite easily. We can just multiply by 360 over pi, I believe. So math dot pi times 2. And we need to import math. Import math. Okay. And we have to do this. Okay, I believe this should be the angle in 4 degrees, the angle in degrees. All right, so that was it for today's episode. We saw vectors and how we can use them with their operations to find out stuff about positions in space, and we'll make heavy use of this throughout the series. So I hope you found this useful. If you did, leave a like, follow the channel, and see you next time. Bye.